Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it, planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist. With me today is the man about Mars, Bruce Jakosky, from the University of Colorado. He's our principal investigator of NASA's MAVEN mission. Now, MAVEN was launched in 2013 to study the atmosphere of the red planet. And MAVEN's been in orbit doing fantastic observations of the solar wind. Maybe many in the public don't realize that the sun constantly outgasses in every direction, and we call that the solar wind. And it has enormous effects on our environment. That's what the planets are swimming in. And MAVEN is designed to study that in its interaction with Mars. So what have you found out?
We've been looking at the way that the solar wind and the sunlight hits the Mars upper atmosphere and can drive gases from the atmosphere into space. In effect, the way the sun and the solar wind can strip gases away from the planet. Over the long term, that has the ability to change the climate by removing so much gas from the atmosphere. What we've discovered is, in fact, that is what's happening. The bulk of the atmosphere, the largest fraction, appears to have been removed to space. And that stripping of the atmosphere appears to be responsible for changing the planet from a warm, wet environment early in its history to the cold, dry environment we see today. That's a major change.
What's really spectacular about the data that you're taking and then the visuals that you create globally of what's happening at Mars is where that escape is coming from and what does it look like from a global perspective. Can you describe that?
We're seeing a lot of different processes taking place and all adding up. Hydrogen, for example, comes from water in the atmosphere, and hydrogen is light enough it can just escape to space directly. Things like oxygen, which come from water or from CO2, carbon dioxide in the atmosphere, are not light enough that they can just escape on their own. They need the solar wind to grab them and knock them out. So we're seeing a lot of different processes, trying to understand how they play together. To me, what makes this exciting is that we're looking at the thin, tenuous part of the upper atmosphere, so thin that we would call that a vacuum if we were doing experiments here on Earth. Yet that's where all the action is in affecting the climate at the surface of the planet, the ability of water to flow over the surface, and really controlling the degree to which Mars could have been habitable by microbes.
Some of the processes at Mars are unique in the sense that we don't experience them in and around our Earth because of our strong magnetic field. So you do have a magnetic field instrument on MAVEN, and you have been measuring magnetic fields. What are you finding out?
We have a magnetometer in order to measure the properties of the solar wind as it comes in, and also what I'll call the morphology of how the solar wind interacts with the planet. It turns out that there are regions of the crust that have a magnetic field. Mars doesn't have a global magnetic field, but it has localized crustal magnetism. And those create little pockets of protection over the atmosphere where the solar wind can't hit them. But they cover a very small fraction of the surface. And overall, we're seeing interactions between the solar wind and the ionosphere and the planet that have a significant effect.
What really intrigues me about that remnant magnetic field, that stuff that's trapped in the crust that you actually measure, is it's a hint of the past. What do you think happened to the magnetic field?
Well, you've got it exactly right. Mars appears to have had a strong magnetic field, a global magnetic field early in its history, and that magnetic field is recorded in the ancient crust. The younger crustal regions don't have it, so we think the magnetic field disappeared. The magnetic field on the Earth is formed by motions within the molten iron core. You have an electrically conducting material like metal, and it's moving and it creates a magnetic field. Mars would have done the same thing early in its history, But when the magnetic field stopped, that must have indicated that the core froze out. It became solid. The Earth's core is still molten, is still generating a magnetic field that we see today, but Mars has stopped.
You know, here on Earth, one of the things that everyone knows is that our magnetic field helps organize particles, and we see occasionally aurora when the sun gets really active and hammers our magnetosphere. So there's remnant magnetic fields on Mars, but does Mars have aurora?
It does. And in many ways, it's more interesting than what we see on Earth. Of course, I'm going to say that. Because on Mars, we don't have a magnetic field to stop the solar wind. So the particles from the solar wind come in and can hit the atmosphere directly. So we see aurora generated by electrons that are hitting the atmosphere, and they're spread out over the whole planet rather than concentrated in northern latitudes as on the Earth, northern and southern latitudes. In addition, we see aurora generated by hydrogen hitting the atmosphere, and occasionally we see aurora created as these particles from the sun hit the crustal remnant magnetic fields and get focused into small regions. And that's the most analogous to aurora on the Earth, because it's connected to the magnetic field. But most of the aurora on Mars aren't connected to the magnetic field.
You know, one of the spectacular moments that we had in planetary science was the passage of an Oort cloud comet right in front of our planets. You know, we think about how that may influence our climate, our activity by being hit by objects, but here is a comet, you know, and indeed Siding Spring passed by Mars. What was that like in the MAVEN data?
Well, let me start by telling you what we thought when we heard about Comet Siding Spring for the first time. It was discovered about a year and a half before MAVEN launched. And when it was initially discovered, they didn't know the orbit well enough. There was a chance it could hit Mars. And my first reaction is, oh my God, if it hits Mars and we're in orbit around it, the debris sent up by that impact would destroy our spacecraft. Fortunately, as they learned more about the orbit, they knew it would pass close, but not hit it. And the orbital dynamics was such that MAVEN would get there a month before the comet, and there was nothing we could do about it. We were worried about surviving the comet passage because of all this dust that comes off the comet. And we debated, should we put extra shielding on the spacecraft? What should we do? In the end, we did the thing that the engineers were most comfortable with, which was nothing. We took no precautions on the spacecraft, but operationally we did. When we were in orbit around Mars, we timed where we were in our orbit so that we were shielded by the planet for about 20 minutes during the time of the peak dust flux to protect the spacecraft. For several hours, we turned edge on to the flow of dust in order to minimize our cross-section so that less dust would hit us. And we survived. We couldn't even tell that there was a comet there from the spacecraft itself.
Well, you know, that must have been a spectacular event if you were standing on Mars looking up at night, seeing the material coming in, just like our shooting stars here.
We see on Earth meteor showers that are pretty spectacular, but they're left over from dead comets. To have a comet pass this close to Mars, only 140,000 kilometers away, and to have the coma of dust and gas hit the planet directly, it would have been a spectacular event to see.
Well, you know, I was delighted that all our spacecraft survived, you know, that we didn't have major problems with those. But, you know, there are other objects in orbit around Mars that, as I understand, MAVEN had to avoid. Can you tell us a little bit about your encounter with one of the moons?
Well, let me start with the difficulty we have in orbit, because there are a lot of spacecraft and their orbits evolve with time. And every now and then, the orbit of MAVEN will cross the orbit of one of the other spacecraft. And we call those COLA seasons, COLA for collision avoidance. We occasionally, maybe once or twice a year, have to do a maneuver to make sure we don't come too close to another spacecraft. But recently, we had a collision opportunity maybe that's the wrong way to put it, but a possibility that we would collide with the moon Phobos. And in that case, the orbit predictions were such that we were definitely going to hit it if we didn't take action. We did a maneuver about 5 days in advance of that collision in order to avoid it. So instead of hitting it, we missed it by about 200 kilometers. We have to watch constantly every day to make sure we're not going to hit something.
Yeah, that's unbelievable. You know, it's getting crowded at Mars, so to speak, but in a nice way. This is the way I like it.
Well, today there are 5 or 6 spacecraft in orbit. MAVEN, Mars Reconnaissance Orbiter, Mars Odyssey, the Indian MOM mission, the European Space Agency, Mars Express, and their recent addition, the Trace Gas Orbiter. And these are the ones that are operating today. In addition, there are dead spacecraft, Mariner 9, Viking 1, Viking 2, the Russian Phobos mission. All of these are in orbit, and it's getting pretty crowded there.
Yeah, and Mars Observer, as I remember.
No, Mars Observer sailed on by without stopping.
We're sure of that.
Yes.
Well, you know, Mars is hard. Sometimes we can't always pull off what we want at that planet. I'm here with Bruce Jakosky, my man about Mars, and we're talking about that fabulous MAVEN mission. I'm always interested in how we get into this business. You know, this is an exciting thing to do, and everybody I talk to, there's typically something happens that gives them that gravity assist that propels them into the science that we're doing. What was that like for you?
You know, I was always interested in space, and I remember being a 6-year-old sitting in front of the TV watching the countdown of the first Mercury astronauts in the very early 1960s. But for me, what really set me on this path was when I was an undergraduate at UCLA. I was a physics major, and I got bored with the classes because all they were doing was teaching us tools and techniques. So I started looking around for something else, and I took a planetary science class from Hugh Kiefer, who was one of the professors there. By the end of the semester, I had changed my major. I was working for him on the Viking mission, and that really set me on this path. So it happened to be one class that happened to be offered when I was looking around for something else to take.
Thanks, Bruce. Well, we figured out how Mars lost its atmosphere with MAVEN. Now, here to talk about a couple other Mars mysteries is Michael Meyer.
Good to be here, Jim.
Michael is our lead Mars scientist at NASA headquarters. I'm really intrigued by some of the recent measurements of methane on Mars. Michael, what's going on?
As you might remember, a couple of years ago, when we first started doing the methane measurements, we got all of a sudden, boom, we got this big spike in methane. And then almost as surprising, it disappeared. And you have to kind of go through chemical gymnastics to get methane to show up and get methane to disappear. And so this is the modelers, the atmospheric modelers are just, they're just in a tizzy over this because how is this possible? So as we go along, we get a low background of methane, which is fine because you can expect, in fact, inputs from comet material to be, just enough to give us some methane. But then we found another spike and then it disappeared. And we're not getting any correlation with anything else that's going on as we're exploring. So this is a real mystery. And it is important because you're right. It can be a sign of geological processes where rock is interacting with water. If you can pick the right rock, you get methane generated. And so there would be an active geologic process going on, which would be really interesting.
Equally exciting. Yeah, it's an active planet.
And we know on this planet, most of the methane that we see is biological products. So, of course, that would obviously be very exciting on Mars, too. Either way, it's a mystery that needs to be solved because we have to figure out what the source is.
One of the more spectacular sets of observations that the Mars Reconnaissance Orbiter has been seeing are these reoccurring slope lineae. And there's been some observations in and around Gale Crater that seem to indicate streaks coming down Mount Sharp. What's our current thinking about those?
Yeah, so recurring slope lineae, it's a mouthful for basically it's something that shows up seasonally. And, so in the spring when it starts warming up, they appear. Through the summer, they get longer down a slope. In the fall, they start to disappear. In the winter, they're gone. And the next year, it happens again, and it happens in the same place. And you're going, this looks like water flowing down the slope. But it's hard to explain that being water just because the temperatures are that low. There isn't that much water on the surface of Mars at all because water is not stable on the surface. What's going on? So, yeah, there have been a couple of candidates, recurring slope lineae in Gale Crater, but they're not very good. I think we only have one or two where the jury's still out that they might be, right? But we're finding them all around the planet. Mars Reconnaissance Orbiter has been doing a fantastic job of looking at the surface of Mars and seeing change. And it's only because they've been there for a while that you can see the seasonal progression and digression of each of these things.
Well, we've needed the Mars Reconnaissance Orbiter's capability with its high-resolution imager, something that could see a coffee table, if it's sat down on Mars, to be able to find these because they're only, a few meters wide. They may be football fields long.
Right.
But that just gets averaged away with our low resolution imagers. You'd never see it.
Well, in fact, one of the challenges and why they're still a mystery is with our spectrometers when we're looking at the colors of these things to tell what the mineralogy is and what rocks are, whether or not there's water there. They're really not large enough to get a good spectra. So we don't see a real change in the spectra over the season. So then you have to wonder what's causing this. Yeah. It goes dark, it gets light. What's going on? Because you don't see it with your other instruments. But we know it's real. We know that something's happening, and we don't have a good explanation yet.
So I think we got to go see one. I think we got to get up close and personal, really to understand what's going on. So I think that's in our future. We've got to go visit an RSL.
Well, certainly the candidate ones that we've been talking about in Gale Crater, we have marked out observation posts. So there's spots as the rover goes along, way in the distance, it could see the candidate RSL, will image them, and of course
at higher resolution than
plus,
MRO.
Plus it has spectrometers,
Yeah.
Right? And so it's one of these things where now it can get a different look at it. It can look at it over better periods of time because MRO can only see it when it passes overhead.
Right.
And maybe it's not a good season because it's the dust season. And so, from orbit, it's obscured. Mm-hmm. But from the surface, you may still be able to see it. So we have high hopes as we go along over the next year and we have these observation posts, we can watch it and see whether or not this is this really real, or is this like a shadow that shows up and disappears, or is it really something that's happening on the surface? And then because we can look at it with multicolored eyes, we can get a better handle on what actually is the causative mechanism.
Curiosity's been doing fantastic, and it's really being a pioneer, telling us that there are regions on Mars that could have been habitable in the past. And that means the next mission, right now we call it Mars 2020, is going to have an opportunity to go to those places that Curiosity is uncovering for us that will enable that mission to make even greater progress. So what's happening in that area?
Oh, you said it very well. 2020 is really standing on the shoulders of Curiosity in a couple of different ways. One is using the whole architecture of the mission of the entry, descent, and landing, the rover body itself, that has worked so well. We're doing it again. Good news is that we're adding brand new instruments, we're updating everything, and it's going to cache samples so that when it finds interesting rocks, we have the opportunity to bring them back. So the other thing where 2020 is standing on the shoulders of Curiosity is what Curiosity learns. It's told us that Mars was habitable during the period of time that Gale Crater was formed, or soon after that. Some of the things about the mineralogy, about the rocks, that tells us what the environment was like. So now the instruments that we're sending on 2020 are informed by that. And then picking the landing site for 2020 to go to is informed by what we've learned in Gale Crater and from information we got from orbit, so that we are much more sophisticated on where should we go to get the right rocks that are going to tell us something about the early history of Mars during the period of time that life started on Earth, that life started in our solar system.
We all get into this field in various ways. It's just fascinating to me to see how we just turn our attention into space. What was that gravity assist that pulled you into this science?
You know, it's a pretty tortuous route from me getting interested in science and actually ending up in the Mars program. But I would say the first thing that really got me was I'd been a fan of Jacques Cousteau. I liked the oceans. I had an aquarium. I was interested in that. I like sailing. I like being on the water. Anybody likes being on the water. And I got hired as a deckhand with a treasure salvaging operation off the coast of Florida. That in and of itself is pretty cool. But the big thing was, after I was there for a couple of weeks, the head of the operation fired all the divers because they're just not doing their job. And so then he asked me if I wanted to dive. Sure, I don't know how to dive, but I'd be happy to. And so I got my opportunity to go scuba diving and, help with the treasure salvaging. There it was, my first foray into the subsurface. And it was like I looked at this world, and despite all the TV shows I'd seen and the occasional book, I looked at this, I went, my word, I don't know anything about this world. This is fantastic. Look at all this stuff. I was just blown away by how fantastic it was, even though I thought I knew a lot about the oceans. And that set me on the track of, you know what, I could do this for the rest of my life type of thing. Now, how I got to Mars is a whole different story, but that got me interested in the science and looking ahead beyond just going to college, but graduate school, and realizing that I could actually make a living by learning things. It's great.
Join us next time as we continue our virtual tour of the solar system. I'm Jim Green, and this is your Gravity Assist.